Welcome to the problem-solving set on packaging of DNA chromosome structure. This first question asks, arrange the following elements in increasing order of compactness. So when you scroll through the four options, you see that the first, which isn't compact at all, is a DNA double helix, which in other words is naked DNA. So remember that DNA, when it's just in the double helix form, isn't compact at all into chromosomes. So we're going to write this as number 1, because they're asking for increasing order of compactness. The second one would be the nucleosome. Now the nucleosome is DNA that's wrapped around the histone proteins. And a nucleosome represents about a 6 times compaction. So this is the second level of compaction. Now the third would be the 30 nanometer chromatin fiber. Now again, this is a helical arrangement of the nucleosome, so it's the next step up. So let me write that, helical arrangement. And this is about 7 times more compact than a nucleosome. So you get a total compaction from naked DNA of about 42 times. And then finally, so this is number 3, finally then the last order of compaction, one that is most compact, is the radial loop scaffold. Now remember, this is about 10,000 times more compact than naked DNA. So the order here is A, D, C, B, and this is increasing compaction. And even though, as Professor Schmidt said in the theory videos, compaction, the idea of it is theoretical, but there's a lot of good evidence that proves that this is pretty much true. Question 2. How many molecules of histones H1, H2A, H2B, H3, and H4 make up a nucleosome? So what you have to remember from theory is that a core nucleosome is an octamer, meaning it's made up of 8 subunits. And the core is made up of 4 histone proteins that are present in 2 copies. So the core is made up of 4 subunits, 2 copies each. So really this question is just to jog your memory of the theory of which of these histone proteins are forming the core nucleosome. So if you remember, the core nucleosome is made from H2A, H2B, H3, and H4. So these 4 nucleosomes are present twice. And H1 isn't present at all in the core nucleosome. So I pulled up the picture from the theory video, and if you see, this is the core nucleosome. So you have H2B, H2A, H4, and H3. Now H1 is holding together this core nucleosome, but it's not part of the actual octamer core. So that's why we are saying that there's no H1 in the core nucleosome. Problem 3. Contrast the compaction of chromosomes that exist during interphase versus anaphase. So for interphase, this is the part of mitosis where the cell isn't actively dividing, right? And when a cell isn't actively dividing, that means that the chromosomes are present in the 30 nanometer fiber form. And that's just how it normally is when the cells aren't dividing. And remember that the 30 nanometer fiber is the helical arrangement of nucleosomes. That gives a total of 42 times more compaction than just naked DNA double helix. So I'll just write 42x. So while this is how chromosomes are normally present, you want to know that regions of transcription may be less compact And remember, the transcription is the formation of messenger RNAs from DNA to make proteins. So regions of transcription may be less compact. And regions where gene expression is not happening, or maybe even gene expression is turned off, it may be more compact. So we'll say regions of no gene expression, more compact. Okay? And this should be compact up here. Okay, so that's how it is in interphase. Now when they say anaphase, and they could have said any of the other cell cycles like prophase, metaphase, telophase, when they say anaphase, they mean when the cell is actively dividing. So anaphase, in other words, equals actively dividing. Now when a cell is actively dividing in cell division, it needs to be in a packaged chromosome that's so compact that it can move, right? Because in telophase, the chromosomes are pulled apart, cytokinesis, they have to move into the daughter cells. So when chromosomes are compact in this way, this looks like the chromosomes that we always draw, these chromosomes. That's the level of compaction that we draw when things are going through cell division, and that's how compact they are. So this compaction has the 30 nanometer fiber loops that are attached to the non-histone protein scaffolding. Okay, and this gives a massive amount of compaction where it's almost 10,000 times more compact. And remember that the reason for this compaction is that so that the DNA can move into the daughter cells without getting broken, without getting pulled apart into different daughter cells. It has to be kept together in one package. So that's why when you're going through active cell division, you have this scaffolding, the radial scaffolding. So this is the more common term is radial loop scaffolding. Problem 4. Mitotic cell divisions and embryonic development of Anax junius, a species of dragonfly, occur every 7 minutes. If there were one bidirectional origin of replication in the middle of each chromosome, how many nucleotides would DNA polymerase have to add per second to replicate the entire sequence in the longest chromosome, which is 52 megabases long? So first you have to know that megabases is really times 10 to the 6th. So 52 times 10 to the 6th equals 52 million bases in the longest chromosome. And they want to know the rate of DNA polymerase, or how many bases it needs to add per second, in order to replicate this entire sequence. So what we're going to assume is that replication occurs during the entire 7-minute cycle. Okay, so if you draw out a chromosome, let's say that this chromosome and it has one bidirectional origin of replication. So I'm going to draw that as a replication bubble. So you have this chromosome and you have one replication bubble in the middle. And it's in saying that the entire length of this chromosome is 52 million bases long. However, this origin of replication is bidirectional, meaning that it can go to the left and to the right at the same time. So technically, it's really only 26 million bases along each replication fork, which is 52 million divided by 2 is 26 million. So when you divide this by 2, you get 26 million. So it's really 26 million bases that DNA polymerase has to replicate in the 7 minutes. So in order to find per second, which is the rate they want, we have to convert 7 minutes into seconds. So we have 7 minutes, and you do 60 seconds per minute, and that gives you 420 seconds. And DNA polymerase has to replicate 26 million bases in those 420 seconds. So to find the rate of DNA polymerase, you do 26 million divided by 420 seconds. And this, remember, is bases. So 26 million. So you get approximately 62,000 bases per second. So that means that DNA polymerase has to add 62,000 bases every second in order to replicate the entire sequence of this longest chromosome. So obviously that number is a little far-fetched. Let me write it in kilobases, so it'll be 62 kilobases per second. So that obviously is a little far-fetched, so let's look at part B. It says, in reality, there are many origins of replications on each chromosome that are spaced approximately 5 kilobases apart. Calculate the average rate of DNA polymerase in this early dragonfly ratio. So again, they want it per second. So again, I'm going to draw a chromosome, and now there are going to be many origins of replication. So I'm just going to draw 3, even though there would be many more. Okay, so again, we're going to assume that replication occurs during this entire 7-minute cycle, and we're also going to assume that each origin replicates in a bidirectional way. So again, they would go to the left and to the right, starting from each origin. So because these are 5 kilobases apart, and it's going bidirectionally, that means that each replication fork is really only responsible for replicating 2,500 bases, right? So when you do 5,000 divided by 2, and we divide by 2 because it's bidirectional replication, you're going to get 2,500 bases that you have to do in those 7 minutes. So again, to find the rate, we know that 7 minutes equals 420 seconds. So to find the rate here, we're going to do 2,500 bases divided by 420 seconds. And you get approximately 6 bases per second. So as you can see, compared to 62 kilobases per second, this number is more realistic, and this is probably how it works in normal mitotic cell division.